Excellent. Okay, so got quite a few slides to go through, and I'm gonna butt up against another meeting that I have scheduled at 11, so I'll just quickly get going so we have some time for discussion later on. So the part of the question that I wanted sort of to address is why do soils need to be drained? And A lot of the soils in southern Minnesota and particularly up in the valley, are high clay content. They're composed of glacial till, so their internal drainage is poor. It's very slow. Sometimes we have landscape positional types of things like depressions or foot slopes that just occur across the landscape, and those tend to be a bit more poorly drained. Sometimes the depth of bedrock, as someone was pointing out about southeast Minnesota, not that there's a lot of artificial drainage there, but depth of bedrock can be a complementary reason why we might need to drain. Um, Seasonal high water tables, of course, and seasonal flooding, especially during the growing season where we're thinking about crop production types of things. So basically, I'm going to kind of pose to you that there are really sort of three sort of general types of drainage that we think about. The two that are on the left really are surface drainage kinds of things to some degree, where we're using open ditches or shallow drains in a field, for example. These are pretty prevalent up in the Red River Valley, um, where we can collect some surface runoff into those and we don't have to put in artificial plastic pipe in the ground. Um, so these ditches are typically a conveyance structure, as most people may be aware, um, and try to get moving water off the landscape fairly quickly. The bulk of the work that I've done and the edge of the field impacts over the years has really been this image on the right, where we've got buried pipe anywhere from 3 feet to 4 feet in the ground at various spacings depending on the soil type, um, and that kind of thing. Now, one of the things that I should kind of um, preface some of my comments with is that drainage in the state of Minnesota has been around, and actually drainage in the United States has been around for a very long time. Drainage in the U.S. has been around since about the 1600s, so the 17th century. Here in Minnesota, we actually had our first drainage law in Minnesota before we became a state. So drainage has been really important to the state of Minnesota for quite a long time. And originally, when we think back to the 1850s and drainage here in Minnesota, um, out here in the western part of the state, there is some documentation that I found that I think it was from Yellow Medicine County that said water. The quote is water was the common enemy of everyone because of human health concerns. So these were things related to mosquitoes and those insect-borne viruses that people were getting from a lot of the swamps and wetlands and things that we had at the time. And so there was a really big push to drain those because of human health reasons. Um, so early on, drainage occurred in the state of Minnesota, not because of agriculture, for example, but because of human health reasons. Um, and in addition, as the state grew and cities and towns were popping up and being populated, transportation was really important. So roads, bridges, those kinds of things. There's a lot of transportation infrastructure put in uh, really in the late 1800s, early 1900s, and a lot of areas were drained, and we didn't have the laws now to protect some of those wet areas as we do today. In the 1930s, even though we think of those as the Dust Bowl years, generally speaking, there was a lot of drainage. That was sort of the first big thrust of agricultural drainage here in the state of Minnesota. And then there was a second really big push after World War II. So inorganic sources of fertilizer became prevalent after World War II, and in the early to mid 1960s, there was a lot of artificial drainage put in, and that was kind of probably the biggest period of time, early 60s to early 70s, when the vast majority of agricultural drainage occurred here in the state of Minnesota. So from that standpoint, ag drainage is fairly recent. So when we think about the process of drainage, base flow in this image really kind of reflects groundwater flow, which tends to be pretty slow in most areas. The surface runoff is fast, and anybody who's been around a river in the last few weeks with some of these heavy rains that we've had, anywhere from 3 to 10 or 11 inches of rain, a lot of the ditches, the creeks, the rivers, the streams look like chocolate milk or coffee, right? Because of surface runoff kinds of issues that have gone on. Um, under some scenarios, the tile will kind of moderate that between the fast and the slow flow. And I say under certain scenarios, because under some situations, when the soil is really, really wet and the profile is pretty full and saturated, um, there's a lot of flow that comes out of the tile and it's pretty fast. But there are other times when we've got drier conditions and that tile actually has dried out some of the soil profile, and it actually kind of helps slow some of that surface runoff kind of situation down. So, scenario driven, I could give you cases where, things would be good or bad, reflecting that on tile, whether tile is a good thing or a bad thing in a certain case. So this is another way to look at the response of water flow, say from a drainage system. So if we were just looking at some volume of water under this bell-shaped curve, if we were looking at the site or any kind of landscape in the absence of artificial drainage, the flow hydrograph might look like this, where we have a lot more rapid runoff under certain scenarios. Um, Alternatively, with drainage, we might attenuate that rapid runoff because we may have dried out some of the soil surface and allowed for some of that water to infiltrate and store itself in the profile before actually leaving the system. Now, one of the other things that's really, really key to keep in mind is that a drain pipe buried in the ground is only going to flow when the area around it is saturated with water. So in a lot of years, in probably most years, the vast majority of them, we don't have tile flow occurring 365 days a year. Um, so in 2017, 18, 19, when we had wet years, we have drain flow measurements here in Lamberton, and we have some drain flow measurements from an on-farm site, and we had somewhere between 300 and 330 days during the 18-19 period where we had flow almost the entire year. Now the pipes were not flowing full, right? So if you think about a piece of pipe buried in the ground, might be 4 inches in diameter, that pipe is not necessarily full of water and gushing like a fire hose 365 days out of the year, or even 30 days out of the year. Um, but the site has to be saturated for that to actually work. In 2021 and 2022, we had less than 60 days of drainage that occurred actually here in Southwest Minnesota and Lamberton. The drought has, an effect, an impact on that hydrology from the soil. So um, it's a complicated system, and soils are highly variable, so it's sometimes a little hard to predict this on even a field by field basis, for example. So when we kind of scan out from just the state of Minnesota to look at sort of the upper Midwest, you can see in that picture there that the areas that are red, orange, and green tend to be the highly tiled areas here in the United States. So you're really looking at eastern North Dakota, the vast majority of southern Minnesota, almost all of Iowa, all of Illinois, all of Indiana, all of Ohio, parts of Michigan when you think about the Midwest, and then that area as you go down toward the Gulf of Mexico, right along the Mississippi River, where there's a lot of big floodplains, where there's quite a bit of drainage. So I'm going to talk a little bit initially about some of the benefits of drainage. And some of these are going to show up on the sort of negative aspects of drainage. But drainage allows farmers to be able to get into the field without compacting their soil, so it increases trafficability. It helps with um, warmer, drier conditions for crop establishment for corn, soybeans, wheat, alfalfa, things that we grow here in the state. Um, The third bullet point there, the protection from excessive soil water conditions, is really one that we think about during the growing season. Crops, especially things like soybeans early in the growing season or sugar beets, tend to be really susceptible to wet conditions. And those wet conditions can create situations where we get um, uh, different pathogens that attack the plant and can really harm the plant or even kill it. In the valley, up in the river valley, salinity control is one of the reasons that we think about drainage in places up there, just because we have saline soils, and that can also negatively impact crop production. And of course, there are benefits to yields for farmers when they drain. So just a little sort of sidebar. There was a 50-acre field that we worked with a particular farmer here in Southwest Minnesota. The family's owned the farm since 1868, and one of the fields had never ever been drained, but had been cultivated since the 1920s. In 2009, the grower had decided he wanted to tile that, so I got permission from him to go out and do some work in that field and take some measurements in that field. One of the things that we found is that before crop production, that field frequently had yield loss because of wetness, wet conditions, because of the nature of the soil. They put in tile, and then the very following year, we had fairly similar rainfall conditions. At least the annual rainfall was similar, and the farmer went from basically 148 bushels of corn to 198 bushels of corn. So keeping the perspective that farming is not a hobby or a pastime for most people. It's their business, it's their enterprise, and the soil is kind of their factory, if you will. They're going to want to do everything that they can to improve their production, and putting in tile is one of those things. And 50 bushels today, I think corn's, at least around here at the ethanol plant across from me, is about 630 a bushel. So 50 bushels an acre for nearly 50 acres at $6 a bushel, that's a lot of money to a farmer. Um, there are some water reduction benefits in terms of surface runoff that I tried to highlight in those curves that I showed a little bit earlier. And in the case of thinking about sediment loss, surface runoff, and phosphorus being associated with that, tile drainage can really help in terms of reducing sediment loss and phosphorus loss. Um, and ammonia nitrogen is usually in surface soils before it converts to nitrates, so that's also a positive aspect of it. And many pathogens and pesticides, you don't really see those in subsurface drainage quite so much as you see in episodes of surface runoff. So agricultural drainage concerns, we have a lot of them. I'm a sports person, and so I like to swim and fish and canoe and things like that. So I'm intimately concerned about the water quality issues that we have. So we think about the fishable, swimmable, drinkable kinds of concerns. We also think about the quantity of water as partly an issue to think about, because sometimes we don't have enough, sometimes we have too much. It's kind of like the three bears syndrome. We want it to be just right. And unfortunately, we aren't in control of the weather. And so that gets to be a little bit of a dicey thing when we think about quantity of water. So the main really big drawbacks of drainage that I've been dealing with in my research for the past 25 years is really looking at that water quality aspect of nitrogen and phosphorus losses. Um, the EPA Advisory Board 2008 report said that nitrogen and phosphorus are disproportionately enriched, or the Mississippi is disproportionately enriched with N and P during the spring, April, May, and June. Well, April, May, and June just happened to coincide with the vast majority of the upper Midwest states that I mentioned earlier as having subsurface drainage. So depending on the year, water that comes down either from the tile or from runoff events like we had recently are going to tend to have dissolved nitrogen and, movable phosphorus that might be moving down toward the Gulf. And that has a direct impact on the size of that Gulf hypoxic zone. So I'm going to talk a little bit about reducing nitrate loss to water just quickly, and then we'll go into some of the practices. So these next few slides are from PCA's report and thinking about the nutrient reduction strategy. And I'm just going to focus on the Mississippi River Basin because that's where I have the most impact of the work that I do. So we were looking at our milestones from 2014 when the nutrient strategy came out to 2025, which were basically almost on the doorstep of that, of an additional 12% reduction in phosphorus and about a 20% reduction in nitrogen, to try to achieve those 45% reduction goals that are set by or set for the Gulf of Mexico hypoxic zone. So based on some of the data that we've seen, we've made some progress in some reductions, but not nearly enough. Especially when we look at nitrogen, we're trying to achieve around a 20% reduction, and we've only moved by just under a couple of percent. So we've got a lot of work to do in nitrogen. We're lower at the phosphorus level, but we still have a ways to go, obviously around 27% reduction that we still need to achieve in order to kind of get to that 45% reduction. So you guys might not find this as amusing as I do, but I look at these numbers as job security for myself. I have work that still needs to be done, so it's a good thing. It's just some of these things are difficult to get in place, partly because of costs and economics. So when we look at this, these are the right figure shows percent reductions that we need to get to, and of course you see the Red River Valley and the Minnesota River Basin by and large, in order to achieve the reductions to get to 45% reduction, are pretty high, and when you look at the total reductions in metric tons, the Minnesota River Basin for nitrogen really kind of pops out at you. Phosphorus, really similar. The percent reductions are different and the metric tons are different, but it shouldn't be surprising that where we have the vast majority of ag production is where we need to do the most work and get the most work done in terms of trying to achieve these goals that we have set out in front of us. So now I'm going to jump to talking about some of the edge of field practices that I've been working on for the last 25 or so years. And again, as I go through those, I'll talk a bit about some of the pluses and the minuses. I actually have two slides that are like this, and as I was updating the presentation, I could only find the nitrogen one, so this is the one I'm showing right now. But it's a similar slide for or a figure for the phosphorus nutrient as well here. But this data is data that I got out of the original nutrient reduction strategy. And on the left axis here, basically we have different management practices that could be implemented in terms of trying to achieve nitrogen load reductions. So I've color coded them. The green ones up at the top tend to be more vegetation oriented, perennialized types of situations. The blue ones tend to be more of a really kind of a strictly water management kind of a practice. The orange ones tend to be kind of a little bit in between the perennialized kind of an idea and the water aspect, depending on how you look at them. And then the brown ones all tend to be soil. Now there are some things in here that are not showing up on here. So back in 2014, saturated buffers were not really a thing to be thinking about, and we actually don't have a lot in Minnesota. I'll get to that later, but saturated buffers is another one of these practices that would end up showing up blue up here. So the first thing you notice is that looking at following nitrogen rate guidelines, using nitrification inhibitors, switching to a spring side dress, or switching from fall to spring nitrogen applications. They do move the dial, but they don't get us to anywhere close to the 45% reductions that we need to get. Okay, under the current cropping systems that we have of mainly corn and soybeans. We start getting a bit closer when we think about implementing strategies like bioreactors and controlled drainage and constructed wetlands or restoration of wetlands. I should have up there as well. Um, Cover cropping can get us there, although I'll talk a little bit about that later. But we have some challenges with that. Filter strips, some buffer strips. Um, can get us there because they can help slow some of that water down that may be carrying dissolved nutrient. The biggest bang for our buck is in this, obviously in these perennial areas, generally speaking, where we've got these under natural conditions that are not being fertilized. There is push to put things on the landscape that are perennial that also afford farmers to be able to harvest. So, for example, kernza, another name for intermediate wheatgrass. Um, We've been working with that. Jacob Youngers in Agronomy and Plant Genetics has been working on it. Forever Greens working on that and other crops. And so, there's a concerted push to get to these green bars that end up being more of a win-win. So it's a win for the environment and a win for the farmers that they can still, make a living doing what they're doing and helping out the environment. We're still a ways away from some of these things, especially when it comes to the plant breeding kinds of things. That takes time to be able to get the characteristic traits of the crops and things that they're trying to develop. It takes time. So as I go through um, the 5 practices here on the left, I'm going to talk about bioreactors, controlled drainage, ditches, wetlands, and saturated buffers. I've done research on the top 4. Haven't done any on saturated buffers, but I've got some decent data from Iowa to talk about related to that. And as I go through my slides, I'm going to try to address these 5 issues on the right. So what are they? I want to tell you how they work, where they work, how well they work, and then we'll talk a little bit about benefits and limitations. So we'll talk about bioreactors first. So this is the first generation of bioreactors. Um, Generally, you had a drainage system come in. There's a control structure to help manage the water coming in and out of the bioreactor. There is a pit full of wood chips, so it acts as a carbon source, so that they can be colonized by microbiology, biological films. That as the water that's laden with nitrogen and phosphorus pass through those wood chips, the biology can actually take and denitrify and remove the nitrogen and use up some of the phosphorus in those systems. So originally, these were a horizontal flow type of a system. They only used wood chips. There was some bypass flow. So during those April, May, June periods of time when we have really high flows at times, not all of the water can get treated by the bioreactor. So that's one of those types of limitations. When they work really, really well and removing nutrients. Um, this is a site in Rice County, bioreactor that I'm going to show a little bit of data from, and my colleague Andre Ranavasan shared with me some of this data. So one of the things I initially want to point out is that the data that we're showing is in a cooler part of the year. So this is toward the end of September through the end of October. What you're looking at in these filled in triangles is the inlet concentration of the water coming in milligrams per liter. So some of that water was well above the 10 milligram per liter standard for drinking water, which is that heavy black dashed line. When you look at the outlets of the bioreactor, you see that we're able to keep that below 10 milligrams per liter. So it was about a 42% reduction based on that little bitty snippet of data that we've been working on here in Lamberton. We put these essentially at the outlet of a tile. So most of those tiles are at the edge of a ditch. Now, I also want to point out that I am a scientist, not an artist. And so ordinarily we would have this type of a bioreactor situated a bit higher above the water level, but I'm not a great artist, so it is what it is. But these were designed for vertical flow kinds of systems. They're filled with wood chips, corn cobs, and we originally looked at these for targeting nitrogen and phosphorus. So we had a phosphorus sorbing material at the top of these bioreactors. So this is the experimental site. These are the replications that we had out in the field for looking at it. And here's the water quality data that we have from that. I'm just going to spend time talking about the 2016-17 data in the essence of kind of looking at some of the time here. And this is only the nitrogen reduction data that we had, but the crushed concrete, limestone, and steel slag, those were the phosphorus reducing materials that we had in those bioreactors. And we had really decent removal of nitrate in the first year of the bioreactors. It declined quite a bit in the second year. Um, the second year, 2017, was a little bit during the growing season, was a little bit drier for us. So it kind of wasn't too surprising that we saw this reduction. We also know that the corn cobs and the wood chips behave differently in terms of their ability to supply carbon to the microbes that are trying to break down the nitrogen. And we looked at our corn cobs, and in year two, the corn cobs, the easily labile carbon had been used up. So we also think that in addition to the weather pattern in 2017, that a lot of the really easily degradable carbon was gone, and so we did see a reduction in the nitrate loss in the second year using that bioreactor. So to kind of summarize, we see that with bioreactors, minimal cropland is taken out of production. They don't require a lot of maintenance, but there is some to maintain the wood chips or the corn cobs that you have in there, and they do show a pretty high capacity to remove nitrogen in particular. There have been concerns about greenhouse gases and methyl mercury. We know how to manage these systems for methyl mercury, and at times of the year, we can see some greenhouse gas emissions come out of these, um, but it's kind of short term. There is a lot of bypass flow that can happen during high flow periods of the year that water never ever gets treated. Um, there are some questions about longevity of the carbon source if these things dry out. There's a lot of chemistry and biology that go on in terms of how long are the carbon from the wood chips going to last, and then we also think about scalability as to how big of a bioreactor would you need, say for 100 or 200 acres. They work. They have some limitations. One of the other limitations that has been pointed out to me, which is also a real limitation, is that from an ecosystem service standpoint, we really only have one really identifiable ecosystem service from this practice, and that is the water quality benefit aspect of it. Controlled drainage is another thing that we've done for quite a few years, and incidentally, that 50-acre field I was describing early on, where we had 150 bushels of corn essentially before drainage, and then after drainage we had nearly 200, is this particular field right here. So the practice of controlled drainage is a practice where a drainage system is installed in a field, and we use one of these control structures at the outlet of the field to try to help manage the elevation of the water table in the field. So during the early part of the season, when farmers are planting or when they're harvesting, we would like to draw the water table down that's in that field so that we can get decent trafficable conditions. During the non-growing season in January through March and then October through December, we like to manage the water level as high as we possibly can without creating surface water in a field. That reduces the loss of water and it reduces the loss of any dissolved nutrients in that field. And then during the growing season, we like to try to look at managing those types of systems somewhere about 2 to 2.5 feet below the soil surface, which helps build up the amount of water that can be stored in the soil profile. so that the roots can actually grow down to that. And initially, when we looked at this practice, we were really kind of hoping for a win-win. So we would have, on the one hand, a win for the environment because we'd reduce nutrients. On the other hand, we'd have a win for the producers because they'd be able to hopefully have stored some water that then would be able to help increase crop production. As it turned out, well, I'll get to the as it turned out when I get to the advantages and disadvantages at the end. So we just published a couple of papers on this. So this is a 100-acre field down there. This zone on this right side of this image that you see is the conventionally drained zone. The side on the left is the controlled drainage zone um, that we had at the Brian Hicks farm between 2006 and 2017. When we look at the overall nitrogen loads, for example, in this, um, the the control drainage to the free drainage, when we look at the volume of flow, the free drainage had a lot more volume of flow coming out. There was like almost 6 inches of water that came out of that field compared to 2 inches, which came out of that field where we had controlled drainage. So it was really helpful for storing water. And we also saw from a water quality perspective that we only had about 4 pounds per acre per year coming out in nitrate from the controlled drainage side versus about 12 from the conventional free drainage side. Um, so we did see a water quality benefit and a bit of a water quantity benefit. So we thought, well, if we have some water stored there, we might see some differences in yield. Well, unfortunately, that did not come to realization over that entire period of time. We only had 1 year of soybeans, and it looks like there was a modest, very, very modest, slight increase even in soybean yields, but not enough to really be statistically significant. Corn yield, again, even though there's a slight decline where we have free drainage from controlled drainage, there's really not much difference here. And in fact, one of the things that we realized over the 11 years where we worked out there is that if we don't manage the water well in a controlled drainage situation when conditions are wet, like we've had this spring, for example, or 2018, 2019, we can actually lose yield from a farmer's standpoint because we hold too much water back, and it can negatively impact the roots. It can create some of those pathogen problems that we don't want to have out there. The other side of it is that during moderate drought conditions, so not severe droughts, but moderate drought conditions, we actually can see a yield benefit from anywhere from, say, 4 to 15% increase in yield. That's kind of what our papers that we just published bore out, that we always get a water quality benefit. We don't always get a yield benefit, and we can actually have yield reductions if these systems are not managed well. Now, the thing that I'll tell you then is that uh, we do see a benefit of reduced drainage volume, nitrate loss reductions, phosphorus load reductions from controlled drainage, modest yield increases. Um, but we also have some negative aspects of this. These limitations are if things are too wet or if they're too dry, we could have some negative impacts on crop growth and establishment. Um, these things do have to be managed and maintained. Active management is important. If we have a wet year during the growing season where a grower may have to, lower the water level in a field, for example, it's going to take some effort and management to get out there and do that. The main limitation of this practice is that it's a topographic limitation. The fields where this can be implemented have to be very, very flat, like almost tabletop flat. Can put them on slopes up to 2%, but then the contractors need to be trained in putting the tile in on the contours of the field in order to be able to make this actually practical and actually make the system work. So um, it is, and it's also a bit more expensive to do because it requires more tile in there to manage the water table at an even level compared to just free drainage, for example. Um, it works well under modest drought conditions, and again, we have some questions on return on investment, especially when we think about that modest yield or slight yield increase with controlled drainage.
Jeff,
Oh, yes.
question about that. That's a system that's used in the Red River Valley.
It has, well,
Yes.
yes, when they started putting tile in up in the valley, A lot of the systems, I think, were put in with the intention of using controlled drainage on those systems, yes.
Okay, so again, the landscape makes a difference in the success of these
Yeah,
practices.
yep. It's
Yeah.
much more conducive up in the Red River Valley because those fields are so much flatter, of course. Um, but it is, you know, if any of you have ever spent any time in the valley, you know, once that river decides it's going to flood, whether you have controlled drainage there, conventional drainage there, or any drainage there, it isn't going to make a difference because the river's going to flood 30 miles and you're just going to have to be at the mercy of the river. But um, when things aren't kind of in that chaotic state, you know, being able to manage the drainage is actually a good thing. So the river valley is the prime place where we would expect to see this practice. Thanks for that question. Okay, so drainage ditches. I think when Rich was talking a little earlier, he used two terms that I've been using, or one that I've used quite a bit, limitations. So thanks for that help with me there, Rich. We're on the same page. This is one of those practices that I use the word opportunity, and Rich used that word as well, that we have some opportunities. Um, so here in the state of Minnesota, these are 1999 numbers. We've got about 27,000 miles of drainage ditch, and I call these 27,000 miles of opportunity. Um, so there are a couple of different states of looking at drainage ditches. The one on the left is down here in Murray County, Minnesota, about 25 miles from me. Um, Beautiful looking ditch. Um, this other is actually also in south central Minnesota, and this has more of a meandering channel that looks more like a stream rather than just a straight channel that you see here. And so this one actually has some behavioral characteristics that are more like a natural stream with this little bitty floodplain here that can be actually fairly advantageous. Now this one's natural, so when some of you may have heard about two-stage ditches, this would be kind of a natural two-stage ditch um, that exists out there in Minnesota. And Bruce Wilson actually gave me that picture. So I'm going to talk a little bit about both types of ditches, although the majority of ditch work that I've done has been on conventional ditches, and probably 99% of the ditches in Minnesota are more of these trapezoidal versions rather than the two-stage type of ditch. Um, so this is just kind of, again, my artist's conception of what these kind of look like from the end view. So the research center here in Lamberton actually has a research ditch facility. It's unique in the United States in that we have constructed 750-foot long drainage ditches. Of course, they're short, so that's one of our limitations on this level of research. But we have a control channel that's managed just as a normal channel. These were designed and built just as a normal ditch channel would out in the countryside. And then we have a treatment channel, which was also built as a normal channel, but we manage the outlet of the treatment channel with what we call a low-grade weir. So basically, it's a little check dam. It's about 12 inches in height, and we actually use that similar to controlled drainage, where we hold water back behind it to increase the surface area to slow the water down for in ditch treatment. We kind of think about these ditches as linear wetlands because they have a lot of vegetation in there. Some sediment and organic material can build up, carbon can build up in these ditches. And so we've conducted quite a bit of research over the years on this type of a thing. For us to actually manage these now, we actually have to do it manually in order to drop the water level in the drainage ditch. But again, this is a kind of my artist's conception. Water flows straight through the control. In the treatment ditch, you see there's this little step down here, and that represents where that low-grade weir would be. So I'm going to apologize, I think, at the outset here, because I think throughout some of these parts of the talk here, I've mixed some units. This is one of those cases where I put the nitrogen in pounds and I left the phosphorus in kilograms. I don't know what I was thinking, but so when we look at drainage ditch work that we've done here in Lamberton, we've seen about a 56% reduction in flow from the treatment side compared to the controlled side. This does beg the question, where does the water go? So we've done some preliminary investigations on groundwater recharge within our ditch system as one of the places that some of the water goes. We've seen a 64% reduction in the nitrate load, and this is over about an 8-year period. The concentrations of nitrate have actually dropped, which is unusual. of bearing out in the data that you see here. Now, one of the things that we look at is for load reductions for the surface flow wetland, from the treatment and the control, even though the numbers are numerically different, we're not seeing statistically significant differences out there. It means there's a lot of variability within the measurements of the system. The same thing with the vertical flow system. Uh, we're seeing actually an increase in load when you go from the surface flow to the vertical flow, and then a larger increase, at least in the control, from the horizontal flow system. But the horizontal flow system is the only one that we saw a statistically significant difference between the control treatment and the treatment of holding more water back. What is really quite interesting is the concentration data for phosphorus and nitrogen. The surface flow actually has the lowest flow weighted nitrate concentrations coming out of it. It increases slightly with the vertical flow system, and the horizontal flow system has the highest concentration. And this is really indicative of the length of time that water is stored in these systems. So the water's got a longer hydraulic residence time in the surface flow system. It flows faster through the vertical flow system and even faster through the horizontal flow system. So this just tells us that the faster that the water flows through, the less likely we're going to get better and better treatment. So slow water, best treatment; fast water, not as good a treatment. The phosphorus, we're actually seeing an inverse effect here. So the surface flow style wetlands actually are discharging more phosphorus than, for example, the horizontal flow or the vertical flow systems. So we're able to actually get the phosphorus to be retained in these systems better than that surface flow condition. And a lot of that is just related to the management and the nature of how those are operating. So we know that wetlands give us a great mitigation of sediment and nutrients. They reduce peak runoff. They have lots of ecosystem services, of course, carbon sequestration, habitat, biodiversity. If we're building them, there's construction cost limitations. If we're restoring wetlands, we've got to find farmers that are interested in doing that, because it'll, you put them in the middle of a 160-acre field and you got a 10-acre wetland, it's going to disrupt the continuity of farming. And so they'd be less likely inclined to maybe do that. And of course, loss of land for production from the farmer standpoint. So there are some benefits and limitations. Definitely, wetlands have, like I say, a lot of ecosystem service potential there. Saturated buffers, the last thing I'll talk about here, which I have not done research on. There's limited research in Minnesota. Most of it's been done in Iowa. Basically, you have a drainage system in a field. You use one of those control structures that I've shown several times. But then what you do is you actually use that control structure to discharge that water back into that grassed buffer or woody buffer between the field and, say, for example, a ditch or a stream. And then you allow natural processes like, for example, denitrification to occur to reduce the nutrients that are in that water. So Iowa has 19 site years. They've reduced their nitrate in those systems by 43%, which is in that realm of what we would like to see in our nutrient reduction strategy. Illinois has seen a similar reduction capacity, about 48%. They have 10 site years worth of data. Ohio and Minnesota, we have at less than half of those numbers of site years. I could not find in the publications that I'm citing here the nitrate removed, but I did find reduction capacities. And these have fairly high reduction capacities. And my sense is that over time, as we integrate all of the different years worth of data, that the numbers for Ohio and Minnesota would probably come down into this 43 to 50% range as you gain more site years. So from a visual standpoint, I'm going to talk about limitations and benefits, but I wanted to kind of visualize this for everybody. Because as the question came up earlier about controlled drainage up in the valley, site suitability can be a really big limitation for having a saturated buffer. Again, saturated buffers are going to have some water quality benefit and some benefits with ecosystem services, but topographically speaking, there are places that are going to be conducive to building these and places that are not conducive to building these. So hopefully you can tell really clearly that where we have a steeper gradient between a field and, say, for example, the elevation of the tile outlet, um, these tend to be sites where they're suitable for building these. Uh, Mainly because you can get water into the soil and move it away fairly quickly. If you have a flatter landscape, which is unfortunately the case in a lot of places here in Minnesota, the landscape is rather flat. And by trying to collect water from the field and then drain it back into the ditch through a saturated buffer, we have two potential problems. One could be water moving back into the field, and the second one could be bank instabilities here. If we get too much pore water pressure on these banks in a flat landscape, it could actually cause bank failures and create problems that we don't want to have. So site suitability for saturated buffers in Minnesota would be a really important criteria for siting these kinds of things. So the benefits, based on the data that we've looked at and that I looked at for this presentation, is they're very effective for nitrate removal. If not sited correctly, they can impact the adjacent crop field, and they have these ecosystem services, as I mentioned. Banking stability can be a limitation. Soil texture would also be an issue. So in areas where we have sandier, coarser texture soils, definitely not suitable. Those are going to be quick to fail. The soil requires a level of carbon. The rule of thumb is about 1.2% at 2 foot of depth, which actually is not a lot of carbon, but that's really what helps drive the system in terms of reducing the nitrate, is having that carbon source there. Um, and one of the things that has been found is that woody vegetation in the buffers, as the water moves through, where the distribution pipes are for these systems, woody vegetation does tend to actually have roots get into those tile and clog them up. So the grassy ones, we've not seen that, but the woody vegetation does have a propensity to actually get in and kind of mess up the drainage system where you have a saturated buffer. Um, Economically speaking, and I'll have all these slides shared with Paul, so everybody will be able to kind of take a look at them. Um, Cover cropping, although I didn't talk a lot about it, is the most expensive practice. And here in Minnesota, we struggle with establishing cover crops. For example, here at the Research Center last year, because of the drought, we tried to establish cover crops in a number of fields, and we have very poor cover crop establishment. Um, Controlled drainage, bioreactors, constructed wetlands, and saturated buffers are all in that roughly a dollar per pound of nitrogen removed, so they can be fairly efficient. And this came from a publication back in 2013. Uh, I'll kind of leave you with this. There's different ways to think about this. Um, we can think about nutrient reductions by practices. So these are like representing just the nitrogen practices. If you remember that bar chart that I showed early on with the brown bars, the green bars, and then the blue and the orange bars. And as we implement those, we can kind of increase the reduction of nutrients. Another way to think about it is to like start mixing and matching things. So, having controlled drainage and wetlands and perennials in a system rather than having either and have them both, or, like take the whole fruit basket and put it up in there and try to achieve uh, that outcome. So different ways to think about how we can actually improve some of the water quality here in Minnesota. And I will stop. Paul and Rich, I've talked way too long, and I apologize for that, but I had a lot to say. So
Great content, Jeff. I think it was really helpful stage setting at the beginning as well.
thank you.
Do you have a hard stop? You got to get to your next one at 11.
Yeah, I can go over by about 5 minutes. So I've got about 7 minutes according to my clock.
Um, we can maybe have time for like one quick question, and we'll go to break and come back with a discussion. But if as we come back for discussion, I'd really like the group to think about like what are some actions the council can take, right? I think Jeff identified some barriers, right, to adoption. And so I'm really interested in, are there policy things, are there things that complement what the Clean Water Fund does? So any questions for Jeff before he leaves, that'd be helpful in our discussion after break.
So Jeff, I would ask what you are finding